2022 AP Calculus AB free response question number 5. Consider the differential equation dy dx equals 1/2 sine of pi over 2x times the square root of y plus 7. Let y equals f of x be the particular solution to the differential equation with the initial condition f of 1 equals 2. The function f is defined for all real numbers. At this point, I'm just going to scroll down at a slow pace. You can pause at any point to take a look at each individual part of this question, A through D. So for part A, we're going to be sketching a solution curve on a slope field. When we get to part B through D, we can pause here. B, we're writing an equation for a tangent line and using that to approximate a function output. For C, we're going to continue from what we learned in part B to determine if we have an overestimate or underestimate. And then for D, we're using separation of variables to actually find that particular solution to that differential equation that's given. So if you'd like to pause this video and try A through D on your own and see how you do, not a bad strategy, but what we're going to do is break down each part on each slide that we go through. So let's begin with part A. A portion of the slope field for the differential equation is given below. Sketch the solution curve through the point 1, 2. So we're given point 1, 2 on our slope field, designated by that black dot. When we draw our solution curves on slope fields, one main thing to pay attention to is the symmetry of our slope field if there is some symmetry present. In this case, we have some line symmetry across the y-axis. Therefore, when we draw our solution curve, your curve should also demonstrate line symmetry about the y-axis. So we're just going to follow the curves here. Each of these little segments represent the slope at that given coordinate. So if I just follow this curve, I'm just going to stop here. So there's the right side of my curve. I want to draw the left side so that it's a mirror image, okay? Because once again, the slope field is demonstrating some symmetry. I'm going to do my best here to maybe plot a couple points that would show that symmetry to help me out. So maybe something like that. So we have this nice smooth solution curve passing through that given point, super important because it is a specific solution curve through a given point. Having the symmetry, something to always pay attention to on a slope field question on the AP exam. And that's all there is to part A. So we have drawn the curve, that's all it asked for through the given point. So let's move on to part B. Write an equation for the line tangent to the solution curve in part A at the point 1, 2. Use the equation to approximate f at point 8. So how do we write a line tangent to a curve? Well, we need to know in general how to write linear equations. We're going to use point slope form because to write a linear function, all that we need are two pieces of information, a point that the line passes through and its rate of change. The point that it passes through is given to us, 1, 2. How are we going to find its rate of change or its slope, which is designated by the letter m? So we can rewrite this if we'd like. That m is going to be coming from our derivative for our function f, which was given to us. We have this differential equation dy dx, and we're going to evaluate that at the point 1, 2 to determine what the rate of change of our tangent line is going to be. The y and x with the subscripts of 1 is where we're going to input the point that it's passing through. So we're going to have y minus the y coordinate of the point, minus 2. Now we have to figure out what dy dx is, evaluated at 1, 2. So we're just going to plug in 1 and 2. So we're going to get 1/2 sine of pi over 2 times 1 times the square root of 2 plus 7. So what's that going to get us? So we're going to have to know our general unit circle on the AP exam. This is a non-calculator question. So we'll evaluate sine of pi over 2, which is just 1, and then the square root of 9, which is 3. So in the end, we get 3/2 for our rate of change. So our slope for our tangent line is 3/2 x minus 1. We can clean this up a bit. So this is our tangent line equation, so it's fine to use that, but ultimately we're trying to make an approximation for the function at 0.8. So we're going to have to evaluate this tangent line for an x value of 0.8. So I'm just going to solve this equation for y and kind of reorder some stuff. So we're going to have 3/2 x minus 3/2 plus 2. So when I distribute that 3/2 and move the 2 to the other side, then if I add these like terms, these constant terms, we're going to get 1/2. So now I've reformatted this so it's in a slope-intercept form. Our goal is to approximate. So f of 0.8 is approximately 3/2 times 0.8 plus 1/2. Now on the AP exam, you don't have to simplify arithmetic, so we're good there. But if we do want to clean this up a little bit to get a nice clean answer, we can convert over to fractions if we want. So 3/2, 0.8 being 4/5 plus 1/2. So we're going to get approximately, let's see, we're going to get 12 over 10, which is 6 over 5, plus 1/2. And then we're going to get 12 over 10 plus 5 over 10, which is approximately 17 over 10. So there's your approximation, or we could say 1.7. So either of those answers fully simplified there, but again, from what I understand, arithmetic not necessary to simplify on a non-calculator portion. So here's our final two answers. We've estimated what f at 0.8 would be using the tangent line. How do we get a tangent line? Quick recap on that. Writing a linear function requires two pieces of information: a point that that line passes through and its rate of change. Its rate of change is going to be determined by the given derivative of the differential equation dy dx. We evaluate it at the point 1, 2. We substitute that in for our m value in our point slope form that I wrote up here originally. And then if it just asked for the tangent line, we could stop at the boxed part, but we ultimately need to make an evaluation. So I move some things around, put it in slope-intercept form to make that approximation. So now let's move on to part C. It is known that the second derivative of f is greater than 0 along the interval -1 to 1, both inclusive. Is the approximation found in part B an overestimate or an underestimate for f of 0.8? Give a reason for your answer. Well, if f double prime of x is greater than 0, then f of x is concave up on that interval. Okay, so that's the first thing we should recognize. Now, visually, concave up means that as the function increases or decreases, it's increasing and decreasing at an increasing rate. That's the definition. So visually, it's going to look like either that or that, where it'd be decreasing at an increasing rate or increasing at an increasing rate. So if we have some tangent line, so let's say our function happened to be decreasing at that point or increasing at that point, your tangent line, 0.8, you'll see, is not exactly at that 0.12 that we were using. So it's a little off, and you would see if I zoomed in, maybe I'll draw a better picture here. So when you have a curve that's concave up, and you have a tangent line that's running towards it, or to a point, and we're using that tangent line to make an approximation. Now this point was at 1, 2 on our curve. We're trying to approximate 0.8, which would be a little bit to the left. Okay, so that point there has an x value of 0.8. So what is our tangent line going to be in relation to the actual function output? We can see that the tangent line would give us an underestimate. And the reason, once again, is because the curve is concave up. How do we know it's concave up? Because we were told that the second derivative is greater than 0. So that would be our reasoning as well. So we can say that we're going to get an underestimate because f of x is concave up on the interval -1 to 1. So our tangent line, as you can see, is below the curve for any point that is not the point that it's running tangent to, or the point of tangency on the curve. So it will be an underestimate for any piece that is concave up. So now let's move on to part D. use separation of variables to find y equals f of x, the particular solution to the differential equation with the initial condition f of 1 equals 2. So this is the difficult part of the problem. When we're trying to use separation of variables, we want to move our x's and dx's to the same side, y's and dy's to the same side. So we're going to manipulate this differential equation that's given to us to reflect that. So I'm going to divide both sides by y plus 7, and I'm going to multiply both sides by dx. So we're going to have 1 over the square root of y plus 7 dy is equal to 1/2 sine of pi over 2x dx. So we have separated the variables successfully. Now, to determine what the particular solution is at this point, we're going to need to integrate both sides. So when we integrate both sides, I'm just going to reformat this equation on the left so that we have the integral of, so the square root is the same as to the 1/2, and then I'm going to move it to the numerator. So we're going to have y plus 7 to the negative 1/2. And the reason why I'm reformatting it like that is because anytime I can reformat equations as a power function, we know that derivatives and integrals are much easier to work with. The most simple rules are applied to power functions, so we always want to be working with those. Okay, so now how do we actually integrate? Well, we're going to take the antiderivative, but what we're going to notice in both sides of this equation is that the functions that we're going to be finding the antiderivative of, they have a composition. But the good news is that we don't need to use a u substitution here. So we are going to have to undo the chain rule due to the composition of the functions. But because the derivative of the inner function is just a constant, we don't have to go through all the trouble of writing out all the u substitutions off to the side, because we're not going to get a cancellation with some other function variable anyway, because of that inner derivative being a constant. So how are we going to take the antiderivative? Keeping the chain rule in mind. So just quick review of the chain rule. If we have function composition, we can find its derivative by differentiating the outer function still composed with the inner function times the derivative of the inner function. So to undo that, we're going to first divide by the derivative of the inner function, then take the antiderivative of the given function still composed with the inner. So let's do that on the left. What is the derivative of this inner function with respect to y? Well, the derivative of this inner function is just going to be 1. So dividing by 1 is not going to do anything, so we don't have to think about that. So now the next part of undoing that chain rule is we're going to anti-differentiate this function still composed with that inner. So y plus 7 is still going to be in the inside composition. Now how do we do the antiderivative with the power rule? Well, power rule, remember when we're taking the derivative, you move the exponent to the front and then subtract 1. So now we're going to add 1 and then divide by the new exponent. Okay, so when we add 1, we get positive 1/2. And now we have to divide by 1/2, which is the same as multiplying by 2. So I'm going to get this. So that is the antiderivative of the left side. Now I'm not going to do the plus c because we only need it on one side. I'm going to keep it on the side with the x, okay, because it would be redundant to put it on both. So now we're going to go through that same procedure over here. We do have composition again, but our composition's derivative is a constant. It's pi over 2. So u substitution we don't necessarily need, but we are going to have to undo the chain rule. So to undo the chain rule, the last part of doing the chain rule is by multiplying by the derivative of what's inside. So to undo that and anti-differentiate, we have to divide by the derivative of what's inside. So we're going to divide this function by pi over 2, which is the same thing as multiplying by 2 over pi. So we're going to get 1 over pi, because I'm going to multiply that constant out front, 1/2 by 2 over pi, and that simplification gets us 1 over pi. So then we now have to anti-differentiate this function, still composed with the inner. So it's still going to be composed with pi over 2x. The antiderivative of sine is negative cosine. And then we have the plus c, the constant of integration. So at this point, we have successfully taken the antiderivatives of both sides, and we now have to find the particular solution, which requires us to ultimately solve this for y. But first, we need to find a value for c. So at this point, to find the value of c, we're just going to use that initial condition. We know x is equal to 1 and y is equal to 2. So if I plug that in, This will allow us to get the value of c. Now, although this may look intimidating, that antiderivative, the good news here is the cosine of pi over 2 is 0. So this whole right side is just going to become c. So whatever the left side simplifies to is our value for c. So 2 plus 7 is 9. Remember, 1/2 is equivalent to taking a square root, so we're going to get 3 times 2, and we find out c is 6. So now that we know c is 6, we're going to go back to this part. We're going to input 6 for c. And our last objective of this is to actually solve this equation for y, but you don't have to get too crazy with all the simplifications. Just move everything from the left to the right so we get a y equals format. Again, we don't have to simplify arithmetic on the AP exam. So if I divide everything by 2, or the same thing as multiplying by 1/2, we can start there. So we're going to get negative 1 over 2 pi cosine pi over 2 x, and then plus 12. Okay, so, plus 3. So multiplying this whole side by 1/2 to clear out that 2, that's what was done there. So there's 2 parts to that right side, right? We have this first cosine piece, and we have this 6. So multiplying both of those by 1/2 gets us the line below. Then we have to square both sides to get rid of that exponent. So y plus 7 is equal to, and all we're going to do is, as you know, squaring both sides, if we wanted to simplify this, would require a double distribution expansion of that binomial, but we don't need to do that. So an unnecessary step and causes a lot of room for error. So all we're just going to do is show that that whole side needs to be squared. And then finally, we're going to subtract 7. And now we have found the particular solution for that a given initial condition, along with that given differential equation that we started with. So that is number 5 on the 2022 AP Calculus AB exam.